In this lesson, we're going to be looking at the trigonometric values for special angles. We're going to start where you left off in geometry with special angles. So this says the two special triangles you learned last year were, and I'm probably going to have trouble fitting this, but we learned 30, 60, 90 triangles and 45, 45, 90 triangles. So we have pictures of them down here. It says they are called special because they have specific ratios between their sides. Since all 45, 45, 90 triangles are similar, so no matter what size I make them, all of their angles are the same and all their sides are in proportion. And the same thing holds true, all 30, 60, 90 triangles are similar. The size does not matter. The ratios are always true. So for example, and we're going to be finding these values, the sine of 30 is always the same value no matter what the size of the triangle is. And that's true for all angles, but we're really going to be seeing it today. These ratios are shown in the diagrams below. Label the equivalent radian measures of each angle. So when you have a 45, 45, 90 triangle, the two legs are equal or congruent, basically because this is an isosceles triangle. And then the hypotenuse, if we went through Pythagorean theorem, we would see as x radical 2. So this x could take any form, any number, but these ratios would hold true. In a 30, 60, 90 triangle, it's true that the shortest side across from the 30-degree angle is half of the longest side, or the hypotenuse. So this side would be an x. So for example, if it was a 5, the hypotenuse would be a 10. The third side, the other leg across from the 60-degree angle, is whatever that value of x is. So if it's 5, this would be 5 radical 3. And if you remember from the last lesson, there was actually a triangle like this. We had a 5, 5 radical 3, and a 10. So moving up the page, the next thing it said was label the equivalent radian measures of each angle. So in this chart, this is not getting into any of the sine and cosine values. Basically, we're going to write down those equivalent radian measures. So if you remember from yesterday or last lesson, we had this piece of the unit circle, and we said that this was 0 and pi over 2, and using different, logical reasoning, when we had 30 degrees, we said that was pi over 6, 45 was pi over 4, half of pi over 2, and then 60 was pi over 3. So we're just going to copy these values into our chart. 30 is pi over 6, pi over 4, and then pi over 3. We're on the next page, we're going to be doing the ratios for sine, cosine, and tangent. Now, if you typed these in your calculator, so for example, if you typed the cosine of 30, making sure you're in degree mode on your calculator, you would get 0.866 and more decimals after that. Basically, it's an irrational number. So you can find these in a calculator, approximated values, but we're going to find the exact values on the next page. So here we have our same two triangles. I'm actually going to go through and do the ratios for the 30-degree angle. It says use the two triangles to find the exact and simplest radical form when necessary, trigonometric values for sine, cosine, and tangent. We're going to use the reciprocal relationships for secant, cosecant, and cotangent to find those. So basically, once we find sine, cosine, and tangent, we'll just flip them over to find the other three. So for sine of 30, if I go to my 30-degree angle, and I look here, my opposite side is x, and my hypotenuse is 2x. So that ratio is x over 2x. Since we don't have any addition in here, I can cancel any common factors. So here, I put a 1x up here so we can see what we'll have. My x's cancel, and I get 1/2. Okay? I'm going to continue with 30 for cosine and tangent. So when I start from 30 for cosine, here's my adjacent side and here's my hypotenuse. I get x radical 3 over 2x. So here, my x's can cancel again, and cosine of 30 is radical 3 over 2. Lastly, the tangent of 30. I need these two sides, right opposite over adjacent. So this is x over x radical 3. my x's cancel. This is a 1 up here. So here I need to rationalize the denominator. So I'm going to multiply by radical 3 over radical 3, which is radical 3 over 3. So those are my first three values. These are, once again, we're going to go in the chart on the other page. So what I'm going to do now is I'm just going to make this page a little bit smaller so we can see the bottom. Okay, and fill in the bottom of our chart. So based on what I already have, sine is 1/2. So cosecant is going to be 2 over 1, which is 2. Remember, cosecant is the reciprocal of sine. Cosine is radical 3 over 2. So we're going to do 2 over radical 3. This one needs to be rationalized. So I'm going to multiply by radical 3 over radical 3, and I get 2 radical 3 over 3. Hopefully yours stayed in the correct spot. And then lastly, the easiest way to do this one, and you really can take it from any point, if I start with this 1 over radical 3 and flip that over, then I don't have to worry about rationalizing the denominator again. So I could have flipped over radical 3 over 3, but that's kind of the fastest way. So what I want you to do is go through and do the same thing for the 45-degree angle. So you'll be working from either of the 45s. You can just pick one. And then lastly, you can work with a 60-degree angle. And from here, you're going to have to erase your opposite, right? And your adjacent. And it's not letting me erase those right now. I'll have to go back and get that just because I changed the size of the picture. So go ahead and work on those. And then lastly, we'll talk about this together. I want you to look for patterns in the values, specifically sine, cosine, and tangent. So we're going to start out with the values of sine and cosine. I know the table is a little messy, but I really wanted to show my work for you. So looking at these, first off, you'll notice a couple things, that sine and cosine of 45 are both the same. And that's because the opposite and adjacent sides are the same. I did have to rationalize the denominator on both of these. For tangent of 45, I have x over x, so it's just 1. So moving over to the 60-degree angle, I did these in black to match the angle here, noting that I changed opposite and adjacent. Something interesting, since opposite and adjacent changed, the sine of 60 is equal to the cosine of 30. And with the same type of reasoning, the sine of 30 equals the cosine of 60. Tangent is flipped here, so I had x radical 3 over x, which gave me, when I simplified, radical 3. So looking across the rows to find patterns, if I look at my sine values, they're all over 2. And then if I look at my numerators, that's counting up. So I have a 1, radical 2, and radical 3. And it actually holds true. If I wrote this as radical 1, it would still work. So I'm going to write square root count up, okay, over 2. Cosine works opposite. So we have still over 2, so that part's not opposite. And we have radical 3, radical 2, radical 1, which is 1. So this is square root count down. It's down here. Tangent doesn't really have any sort of nice pattern. We're going to learn a way to do that in a little bit. Okay, so you probably want to memorize these. Or right now, I don't want to give too much away, but there is a formula we can use here. So I'm going to want to go back and fill in this formula in a little bit. So if I scroll down the page, basically if I look at my cosecant, secant, cotangent values, for cosecant, I just took cosecant of 45. I just took this 1 over radical 2 and flipped it over to radical 2. Same thing with secant of 45 for cosine. And then if I flip over a 1 for cotangent, from tangent, that's still a 1. You'll notice basically the work for 60 degrees is the same as what I did over here. I erased this to fit in the chart better. So these two are opposites, just like sine and cosine are opposites. And then here, lastly, I just took my radical 3, flipped it over and then rationalized the denominator. So for these, I don't even really think about patterns or anything like that. I just do 1 over the sine of theta, 1 over the cosine of theta, and 1 over the tangent of theta. So what you want to do so it's not so messy is we're going to go back to the previous slide, and we're going to add in these values on that page. I'm going to start a new video for that though.